Hi everybody, this is Frank. I hope you remember me. I'm the instructor of your course. I know we can't meet face to face to discuss statistics, but we can still do it online. So what I want to do today is introduce you to the analysis of variance, specifically what we call the one-way analysis of variance. Analysis of variance is often called Anova for short, so that's typically what you'll hear me call it. So right now I'm just going to introduce the basic logic of the Anova. And then in subsequent videos, I'll show you the formulas that we're going to use. I'll show you how to compute them, how to interpret the Anova, and then also how to do something that we call post-tests. So we've got lots to learn about Anova. Let's just go ahead and jump right in. So of course, we've learned z-tests, where we compute z-values, t-tests, where we compute t-values, and now we're going to compute an analysis of variance, where we compute an f value. And that f value is very closely related to a t value. Because if we were to compare two groups, like men versus women, to see who sends more text messages, we could actually use the independent samples t-test or the analysis of variance. And it only makes sense that for both those tests, we should find the same result. I mean, the world wouldn't make sense if we found different results based on picking a different statistical test to use. So the f value that we compute with the Anova and the t value that we compute with the t-test are actually very closely related. Once you know the value of a t-test, you would know exactly what you would find with the f-test. And that's because t squared equals f. Now, anytime we have more than two groups, we can no longer use a t-test, and we would have to use an analysis of variance. So this is where its strength really comes in. Let me give you an example. Let's say we're trying to determine who's most optimistic about our country's future, Democrats, Republicans, or independents. Because we have more than two groups, we couldn't do the independent samples t-test, but we could do the Anova. The reason why we can't do a t-test when we're comparing more than two groups is because more than one difference can be computed, and t-tests are all about computing differences. So look at this situation right here. I'll explain it more in a minute. But we have three different groups, some people who are in a relatively cold room, some people who are in a comfortable room, and some people who are in a warm room. And we're seeing how much information they can learn, how much information they can recall when they're tested. And these values in here show how much information they recalled on some type of follow-up test. My point for right now is simply that when we look at all this data, you see we could compute more than one difference. We can compute a difference between the people in the cold room compared to the comfortable room. We can look to see how much there's a difference between the people in the comfortable room and the hot room. And then we can also look to see how much people differ between the cold room and the hot room. A t-test can't handle that. So if more than one difference exists, we can't use a t-test because the t formula, as you recall, isn't structured in a way to handle that. But analysis of variance is. And this is why. When we do an Anova, we are analyzing variability. Specifically, I'm analyzing variability between these means. Just take a look at these group means for a second. It looks like the people in the comfortable room performed better than the people in the cold room and the people in the hot room. If there are differences between those means, it also means there is variability between those means. If you think about it, the word variance is really just another way of talking about differences. When we have variability in the data, we have differences in the data. Well, if I want to see if there are differences across these three groups, another way I can determine that is by seeing if there's variability between these three group means. So that's what Anova is all about. It's about looking at the variability between the groups. But when we focus on the variability between the groups, looking at the variability between these group means, we need to ask ourselves, where do these group means come from? And of course, the mean for this group comes from the individual performances from these 5 people in that group. And when you look within that group, you can see they all didn't perform the same way. In other words, there's some variability within the group as well. And the variability that we see within the group contributes to that group mean. Just like the variability that we see right here between these scores contributes to this group mean. with analysis of variance, we partition the variability that we see between the groups, so literally the variability that we see between these group means, and we also partition the variability so we can see how much variability there is within the groups, like the variability you see right here within these values, the variability that you see right here within these values, and the variability that you see right here within these values. Because what we're trying to figure out is, does the variability that we see between the groups represent variability above and beyond the variability we would expect within the groups? Because what is this variability within the groups? It really just represents individual differences between the people. It essentially represents sampling error. It's a variability that we can't really put our finger on. It's a variability that we can't really explain. I want to be able to explain the differences that I see between these groups in terms of the temperature of the room. But the variability within the groups is just due to individual differences between the people. Well, maybe the people differ so much that I see these differences between the groups simply because of all that individual variability within the groups. So with analysis of variance, I'm trying to determine, is the variability between these groups above and beyond the variability that I see within these groups? So let me just say that again, because I know it seems somewhat complicated. I keep saying the word variability, but it really comes down to this basic point. I'm trying to see if the variability between these groups, represented by these group means, does this variability between these groups represent variability above and beyond the variability that I see simply within these groups, the variability that I would expect just due to individual differences. So when we talk about variability within these groups, just simply representing individual differences, that's typically in class what we talk about differences we would expect just by chance. So one more time, are we finding differences between the groups above and beyond differences that we find just by chance? Just like everything else in our class, at first things feel a little strange. At first they're unfamiliar. And then as we start talking about things and they become more familiar and we start filling in the blanks, then they become more comfortable. So just give yourself a little bit of leeway. Now, I know students hate talking about the assumptions of these different statistical tests because oftentimes they're confusing, but you're going to be pleasantly surprised. I mentioned to you that the one-way analysis of variance should really be seen as an extension of the independent samples t-test. Well, it makes sense then that the assumptions for the independent samples t-test are the same as the assumptions for the one-way Anova. So let's just quickly go through them again. Keep in mind that these assumptions need to be true for the validity of the test to remain intact. In other words, for us to trust the results, these assumptions need to be satisfied. The first assumption is independent observations, and that means one person's responses should not influence another person's responses. So when I collect data from someone, I want to get their true measurement, not their measurement influenced by someone else's measurement. And remember, that's mostly a research design issue, because if I collect data from people privately, from people who are not being influenced directly by others, then the information that I get should be independent. The second assumption that must be met is that the populations that the samples represent must be normally distributed. So if I'm collecting data from Democrats, Republicans, and independents in terms of how optimistic they are about our country's future, then the data from those three populations on that particular measure, optimism, needs to be normally distributed. So how can I know that? Remember, I can take a look at my sample data for each of those three groups, and I can look at the distributions. If my sample data is normally distributed, I can safely assume that the population data that the sample data represents is normally distributed as well. But if my sample data is horribly skewed, I should probably start thinking that maybe the population data is somewhat skewed. So the smartest thing to do is to look at your sample distributions to determine if you might have violated this particular assumption. Keep this in mind too. Even when we violate this assumption, we can still trust the results of our statistical test as long as our sample size is large. And in this case, we interpret large as meaning in n, a sample size of 30 or more per group. Now keep in mind, that starts getting large. If we've got 3 groups and we need 30 people in each group, we're measuring nearly 100 people overall just to satisfy that assumption. So just keep that in mind. The third assumption is the assumption that most people consider most important, and this is the homogeneity of variance assumption. In other words, the equality of variances assumption. And this is just simply saying that the populations that the samples represent must have approximately equal variances on the measurement that you've taken. So the variability for the Democrats when it comes to their optimism needs to be approximately equal to the variability of the Republicans in terms of their optimism, and that needs to be approximately equal to the variability of the independents in terms of their optimism. So how can we check that? Remember, we've got our sample data. We can look at the variances for each group. And one thing we can do is just a simple eyeball check. If the variability in one group is like 4 times that of another group, then we might have problems. We might have violated this particular assumption. But if the variances differ by less than a magnitude of 4 times, then in general, we don't have much to worry about. There are more formal tests. So for example, there's a test called Fmax, which is very common, and I used to teach that in some other classes. We can use these more formal tests, but in general, we'll just use the eyeball test. I mentioned that we're going to be focusing on the one-way Anova. The one-way Anova is also called a single factor Anova. And all that means is when we use the one-way Anova, we're analyzing data that has one variable that's been manipulated, one factor that's been manipulated. So in the example that I was telling you about, the one factor is political party. And the political parties were divided into 3 groups. So that's just one single factor, one grouping variable, political party. But within that grouping variable, we've got Democrats, Republicans, and independents. But try to see behind that. Even though we have 3 groups, it really just comes from one variable, political party. So another example might be a drug study. Let's say I'm trying to determine the optimal dosage of a drug. So I'm giving people in several different groups the same drug, but varying dosage levels. So one group might get none of the drug at all, just a placebo, so 0 milligrams of the drug. Another group might get 10 milligrams. Another group might get 20 milligrams. Another group might get 30 milligrams. Another group might get 40 milligrams. I've just mentioned 5 different groups, but those groups were being determined by one variable. How much of the drug did the people receive? So that's the one factor. So when we talk about the one-way Anova, the single factor Anova, there's just one variable that's being manipulated. Let's talk about the different hypotheses that we're going to be comparing. Because in all of the statistical tests that we've learned, in step 1, we set up some competing hypotheses. And the null hypothesis always states there are no differences. There is no effect. And remember, when we collect data from a sample, we're trying to learn about the populations they represent. So I might collect data from 50 Democrats, 50 Republicans, and 50 independents, but I don't really care about those 150 people. I care about the people they represent in the entire population. So of course, for our null hypothesis, we will set it up in terms of population means, mu. And of course, the null hypothesis is going to state that the population mean for the Democrats is equal to the population mean for the Republicans, which is equal to the population mean for the independents. So that would just be an example where we're comparing 3 different groups. The alternative, we're going to kind of take an easy way out, and we're going to simply write it as saying at least one population mean differs from another. And the reason we're going to do that is because many different alternative combinations could exist. So for example, maybe the Democrats and the independents don't differ, but they both differ from the Republicans. Or maybe the Republicans differ from the independents and the Democrats. There are several different combinations, and we don't want to have to list them all as alternatives. So the bottom line is this. The null hypothesis is that there are no differences between the population means. The alternative hypothesis is that at least one difference does exist. Now, by the way, that's why later on we might need to use what we call post tests, Because if we find a statistically significant result, and we determine that at least one population mean differs from another, then later on we need to figure out which populations actually differ. And it's the post-tests that tell us that answer. Well, that's enough for now. We've just talked about, in general, what analysis of variance is all about. We've talked about what it represents theoretically. What we need to do next in the next video is get comfortable with the notation that is specific to the Anova and the procedures for computing the F ratio. So we'll talk about that in the next video. Until then, if you have any questions, you can just email me or email the tutors. If email turns out not to be a good way to answer your question, we could always talk on the phone or via Skype or Zoom. There are lots of ways for us to connect. So don't worry about it. Just make sure you get answers to your questions. Take care.